In this example, we're going to go ahead and calculate the area now under a parametric curve. And we're going to do the same thing that we did when computing the arc length or the length of a parametric curve. We're going to go back to our integrals for computing the area under a function that's only a function of x. So stepping away from parameterizations for a moment, when we have y is equal to, say, a capital F function of x, and we wanted to know the area between, say, x equals a and x equals b. So let's just arbitrarily draw some function. Say a to b. Our function does something, but we only care about the area underneath here. The way in which we could figure out this area was just by doing a definite integral. The definite integral from x equals a to x equals b of our function f of x dx. So we are going to take this area formula for functions in kind of a Cartesian representation and go ahead and try to introduce a parameterized version of it. So for a parameterized curve, or parametric curve, again, we'll say this is x is a function of t, y is a function of t. The coordinates are each individual functions of our parameter. We're going to go ahead and take that area integral that's in the Cartesian representation and now try to parameterize it. So let's go ahead and start. And just to make this a little more easier to digest, let's say that our function x of t is equal to little f of t, and y of t is equal to a function g of t. So we'll start off with our integral. X is equal to, the area is equal to the integral from x equals a to x equals b of our function capital F of x. And right away, from earlier, this capital F function of x, we called this y. So we're just going to rewrite that now. So our integral is equal to the integral from x equals a to x equals b of y dx. And in this notation, though, again, this y is a function of x here. So our next move that we're going to make is basically like a u substitution or a substitution type feel. We're going to let y equal the function g of t. That's basically saying, you know what, we're introducing this parameterized version of y. So let's rewrite that integral now. So it's still the integral from x equals a to x equals b of now g of t, and then integrating with respect to dx. And there's a few things for us to fix up here. We still need, we need to integrate with respect to the right variable, and we're going to have to go ahead and change the bounds of that integral. But we are moving in the correct direction. So let's go ahead and try to figure this out. So we have the area is equal to g of t dx from x equals a to x equals b. So let's do a couple things. The first thing, let's integrate with respect to the right variable. Well, if you remember from our previous page, when we parameterize the curve, we said x, the coordinate x, is a function of some function f of t. So you know what? We're basically going to still treat this as though we're doing substitution. We need to get this dx into a different variable. So we'll start off with what we know. We know x is equal to a function of t. That's just whatever our parameterized curve function is for the coordinate x. If we differentiate both sides, we get dx dt is equal to f prime of t. If you've watched the arc length video for parameterized curves, we did the same exact thing for going from dx to dt's. And well, last thing we need to do, solve for dx. Dx then is equal to the derivative of our x function with respect to t times dt. So we're going to be able to substitute this in for our dx in that integrand. The other changes we need to make, and we did this again when we used, or when we're computing the arc length formula for parameterized curves or parametric curves, we need to change the bounds. And the way in which we changed the bounds previously was we needed to find t-values basically for each function. So we need to find a t-value such that x of t is equal to our upper bound. And the function in which we called this, or the value in which we called this before, was we said, you know what, find some t equals beta value such that x of beta equals b. We said the same thing, find a t-value, and we're going to call that alpha. Such that x of alpha equals a. So what we're really doing here is solving for t-values that land us at the right x value, if this was confusing. So let's put this all together now of what we have. So to compute the area under a parametric curve, and let's call that curve, say, x of t, y of t, where x of t is some function of t, just to be sure, and y of t is a function of t as well. We compute the integral of t equals alpha to t equals beta, that's just the upper and lower t value bounds, times the derivative, or sorry, times the function g of t itself, times the derivative of our function f with respect to dt. And just so we're clear, g of t, that is our y, and f prime of t, that is the derivative dx dt. So let's do one quick example of this. And for this example, we're going to compute the area under one arch of what's called a cycloid. This is just one example of a parametric curve. And a cycloid is given, in this case, by x equals t minus sine of t, and y is equal to 1 minus cosine of t. So to put this in perspective earlier, what we previously called f of t, that is t minus sine t. What we previously called g of t, that is 1 minus cosine of t. So let's plot this cycloid. And again, there's no reason by just looking at this parametric curve that you'd know what it looks like. So plotting this on the xy plane, what this parametric curve looks like is the following function. It's basically going to keep rolling along. In both directions. And the direction of this curve is going towards the right. And when we're interested in the area under one of these arcs, what that means is we can choose the arc arbitrarily. They're all the same size. And we'll just choose this first one. So what we need to figure out are the t values at the start and the end of that first arch. So this would be what we call the beta. And this point would be the t equals alpha. In other words, we're looking for the t value that lands us at the beginning of the curve we care about, and the t value that it lands us at the end of the curve or part of the curve that we care about. It just so happens that both of these happen when y is equal to 0. So before we get into all of that, actually, let's just dive right into that first. So let's find the bounds. And in this case, we know y is equal to 0 at both of these bounds. We know x is equal to 0 at this first bound, and we know y is equal to 0 as well. And the second bound, well, we know y is equal to 0. What x is equal to, it's unclear. So let's figure out when y equals 0. So we'll take this information of knowing that y equals 0 at this first point to figure it out. And for that matter, y equals 0 at the second point as well. So taking our equation for y and setting it equal to 0, we can figure out what t values we need. So we're looking for values of t that give cosine values of 1. And well, that's going to be values whenever t is equal to, well, things like minus 2 pi, 0, 2 pi, 4 pi, etc. So the next thing we need to do is figure out, okay, we have possible candidates for t values. We need to go ahead and evaluate our x value or our x function at some of those t values to make sure that we're landing at the correct start and end point of the curve that we care about. So if we take our x value, or our x function, and evaluate it at minus 2 pi. Let's see what happens. Well, when x is equal to minus 2 pi, that is minus 2 pi minus sine of 2 pi. And well, sine of 2 pi is 0, so this is entirely equal to minus 2 pi. And well, this doesn't check out because we need an x value that's equal to 0, and our next x value, while we may not know what it is, we know that it's surely greater than 0 because we're on the right-hand side of that plane. So let's try the next value. When we evaluate our x function at 0. Well, this gives us 0 minus sine of 0. That whole thing, 0. So this one looks like it checks out. So this t equals alpha point, the t value here is actually 0. And again, we only found this point out by figuring out what y values land, or what t values land us at y equals 0, and which one of those t values also lands us at x equals 0 as well. So let's work on the next point. Well, we've already thrown away minus 2 pi. We figured out that 0 is actually our lower bound for alpha, or lower bound for t. So we can try marching higher values. And since we are moving higher values of t, and t is kind of guiding us along this curve, we want to ask ourselves, hey, when t equals 2 pi, is that going to be the next candidate for t equals beta? So let's go ahead and evaluate that. So when we evaluate our x function at 2 pi, we get 2 pi minus, well, sine of 2 pi, which is 0. So this is equal to 2 pi. And well, what can we say about 2 pi? 2 pi is greater than 0. And if we wanted to be sure that this was the next t value that actually lands us at this value here, well, what we need to do is check the other t values as well. And if you go ahead and check the other t values, so for example, trying x of 4 pi, what we would find is, well, all of these t values that are higher than 2 pi, they're going to put us at x values that are larger. So 2 pi looks like to be the next smallest x value we have. So our integral looks like we are going from t equals 0 to t equals 2 pi. But these are the ways we figure out those bounds, setting the x and y values explicitly equal to certain x and y values as well, and making sure that the same t value lands us at the points both in x and y. And then what we need to do is, well, we need to take a derivative, or sorry, not take a derivative, but we need to put our function for y of t here, and we have to multiply that by a derivative of our x function with respect to t. And once we do that, we are allowed to integrate with respect to dt, or with respect to t. So if you remember previously, our function for y was just equal to 1 minus cosine of t. Our function for x was equal to t minus sine of t. So if we take a derivative of x with respect to t, that gives us a 1 minus cosine of t. So we can plug those in. So if we plug those in, we get the 1 minus cosine t coming from our function that was y. And we also get a 1 minus cosine of t coming from the derivative of x with respect to t. And lo and behold, that integral is fully in terms of t. We have all the bounds we need, so we can go ahead and integrate it. And again, at this point, we're at this point in our mathematical journeys where we're presented with hard integrals. In integrals, we can either do explicitly and exactly using all those integration techniques, integration by parts, trig substitution, maybe a partial fractions using trig identities, using a substitution method. Or if we're presented with a very difficult integral in which we cannot find its integrand, we could also turn to integral approximations. But in this case, let's just distribute the 1 minus cosine into the 1 minus cosine and see what we get. So we have that this is 1 minus 2 cosine of t, so far looking like things we can integrate, and then plus a cosine squared of t. Okay, something that we don't automatically know its integral or antiderivative. Well, hopefully remember to earlier in the course, we can integrate 1, we can integrate the minus 2 cosine of t, and for this cosine squared of t, we get to use trig identities. So we'll go over that now. So this is equal to 0 to 2 pi, the integral of 1 minus 2 cosine of t. And the identity we're going to use comes from the half angle identity. And for cosine squared, the half angle identity is 1/2 1 plus cosine of 2t. Again, this is coming from that cosine squared term, or the half angle identity. And once we have introduced that half angle identity, we can actually go ahead and just integrate everything that is there. Or we could do a little bit of cleanup. So for example, this 1/2 times 1, when we add it to the other one that's there, this will give us a 3/2. We still have a minus 2 cosine of t, but then we're also going to get a plus 1/2 cosine of 2t. So let's go ahead and just integrate everything else. Oops. Let's go ahead and integrate. So integrating that 3/2 just gives us a 3/2 t. Integrating that minus 2 cosine t gives us a minus 2 sine of t. And then integrating that 1/2 cosine of 2t gives us a plus 1/4 sine of 2t. And we're evaluating that at t equals 0 and t equals 2 pi. Oops, I forgot the t in that first. 3/2 times t. All right, so we can plug all of this in. If we take a look at this for a minute, well, if we evaluate a sine at either a 0 or a 2 pi, it is going to be 0. If we evaluate sine of 2t at 2 pi or at 0, this is also going to give us 0. So this whole thing eventually comes out to 3/2 all times 2 pi. Or our final answer, 3 pi. So I hope this was informative in how to compute the area under a parametric curve. We started off with the area integral of just like a Cartesian function, where we just have y as a function of x. We then mathematically massage that into a parameterized setting. And the integral that we get for a parameterized curve is an integral in terms of the parameter, in this case t, where we multiply one function or one coordinate's function by the other coordinate's derivative. And we have to make sure that the bounds are with respect to t, and the way in which we find the bounds are making sure that the t values are landing us at the correct x and y values.